Off on Wednesday, and we had talked about dosages based on weight and those recommended ranges. And we had just started talking about dosages based on body surface area when my system shut down on us. So that's what we're going to pick up today. So an example, similar to our dosages based on weight, a typical order might simply read administer recommended dose every 6 hours. And the recommendation might be something like 250 to 300 micrograms per square meter every 12 hours. And then our label on our supply might say something like 50 milligrams in 17 milliliters. And we have a patient, let's say that they are 1.64 square meters of body surface area. Let's figure out where this dosage is going to put us. So we start off with the patient. The patient is 1.64 meters of body surface area. Put that over 1. And then we can see here we have, once again, just like with dosages based on weight, we have a minimum and a maximum in our range. Just like weight, we're going to go with the maximum. So that's going to be the 300 micrograms per meter squared. So over 1 meter squared. And we will notice that the meter squared cancels out, which is what we wanted. Now next we need to get rid of the micrograms. We're looking at how many milliliters, what's our range in milliliters to administer to this patient. We have to get rid of micrograms. Unfortunately, in this problem, there is nothing else that references micrograms, but we do have something referencing milligrams. So this is a standard conversion, so we can just use that standard of 1,000 micrograms in 1 milligram. And now that we're in milligrams, we can proceed to use the conversion from milligrams to milliliters. The milligrams on bottom, and it says 50 milligrams in 17 milliliters. So the milligrams will cancel out. And now we're going to be in milliliters, so let's go ahead and work through that. So on top there, we have 1.64 times 300 times 1 times 17 milliliters gives us 8,364 milliliters. On bottom, we have 1 times 1,000 times 50, so that's 50,000. And we will go ahead and divide that out. It's going to be a really small number, 0.167, we'll round that to. That is milliliters. Now, this is where we have to go back and make sure we take our time frame into consideration. This is per 12 hours. The doctor's order was to administer the medication every 6 hours. So we have to do that titration to change it, to convert from every 12 hours to every 6 hours. So we start off with our value here, 0.167 milliliters. And that was based on a 12-hour dosage. We're converting to 6 hours. And as always, in our titration, remember, these units have to be the same so that they will cancel out. We have our 0.167. I left it in the calculator, so I didn't round it off. So I'm technically using 0.16728 here. Times 6 divided by 12 gives us 0.084. We'll round that to milliliters every 6 hours. Now you'll recall that this is the maximum dose from our range. To find the minimum dose, we'll take that maximum dose of 0.084 milliliters every 6 hours. And that was calculated off of 300 micrograms per meter squared. And we're going to convert it to the minimum, which is 250 micrograms per meter squared. Once again, the units cancel out in our titration ratio there. We have 0.084, and I will punch that back in as 0.084 times 250 divided by 300, giving us 0.07 milliliters. So our safe range here, or recommended range, I should say, for this patient is to administer between 0.07 milliliters to 0.084 milliliters every 6 hours. It's important to have that time frame in there so that we know how often we're administering that medication. So that calculation isn't really much different than our calculation for dosages based on weight. We will definitely come back and do some more examples, but first let's talk about how do we determine body surface area? BSA for short. Well, there are a few methods. There's a chart method, which pretty extensive. There is an electronic app method, which is what a lot of EMTs are using it now. It's an electronic app they have on their laptop or their phone. The two that we're going to look at, look at a formula. The formula uses height and weight to calculate an estimate of body surface area. All of our ways of calculating body surface area are really estimates, because people that are the same height and weight can be different shapes and have different body surface areas. So everything we're looking at is simply an estimate, but it's relatively close. We all know that the composition of the body, a body made of muscle, is going to be smaller than a body made of fatty tissue, just because the fatty tissue takes up more volume per unit of mass or per unit of weight. So like I said, these are not going to be exact, but they're close enough for our dosage calculations. So our first version of the formula is for weight, which technically we know is mass, in kilograms, and height in centimeters. That's important. Weight has to be in kilograms, height in centimeters. So our formula, now N is just, we're going to use that for our body surface area. This is going to be in meters squared, is going to equal the square root of the height times the weight divided by 3,600. So that 3,600 is just a constant that works into this formula. So let's take a look. If we have a patient that has a height of 128 centimeters and a weight of 46 kilograms. Our body surface area, using this formula, is the square root of 128 times 46 divided by 3600. Now, fortunately, we can put this in our calculator all as one big long stream. So second square root. Make sure that if your calculator doesn't automatically put that open parentheses in there, you might have to put it in yourself. 128 times 46 divided by 3600. And we can just put it in as a single line like that. We don't have to separate it out at all. Make sure you close your parentheses to end your square root. And hit equals, we get 1.279. Which we're actually going to round to just 1.28 square meters. Almost all of our calculations go to 2 decimal places when we're looking at body surface area. So that's about as precise as we would ever take that calculation. Well, I'm going to have you guys try one here. I'm going to leave the formula up here where you can see it. And our patient is going to have a height of 1.48 meters. Be careful with that now. And a weight of 90 kilograms. So again, be careful of the units here. That is in meters, so you have to make that conversion first. I'll give you a minute or so to calculate that, and then we'll go through that. So our first step here is the 1.48 meters has to become 148 centimeters. So then our body surface area in meters squared is going to be the square root of 148 times 90 divided by the 3,600. So simply square root 148 times 90 divided by 3,600. Again, we have to make sure we close our parentheses on our square root. It equals, we get 1.92 meters squared. Well, our second formula, or second version of this formula, is if our weight is in pounds and our height is in inches. In other words, if we're using our empirical units or standard units of measure. And here, our body surface area in meters squared again, it's still going to be the square root of height times weight. All that's going to change is this constant. It's not going to be 3,600 anymore. It's going to be 3,131. That conversion's actually really kind of simple. All it is we're taking the 3,600 from our formula up here, and we're converting the units. If I start with 3,600, and I do my conversion for centimeters to inches, plus 2.54 centimeters is 1 inch. Then I also do my conversion for pounds to kilograms. 1 kilogram is 2.2 pounds. We notice here that the calculation is simply 3,600 divided by, because it's on bottom, the 2.54, and then times the 2.2 on top, and there it is, 3,118. Well, there are some adjustments there. We got 3,118. That's because the 2.2 pounds per kilogram that we use is actually very approximate. It's actually 2.2 208 or 21 something, depending on how exact you set that up. So it really is just a conversion of that 3600 to the different units for inches instead of centimeters and pounds instead of kilograms. So that's the units we're going to use. So let's say that we have a patient who has a height of 71 inches and a weight of 168 pounds. So their body surface area in meters squared will be the square root of 71 times 168 over 3,131. So again, in the calculator, it's just square root 71 times 168 divided by 3,131. We close our parentheses, and we get 1.95. This is still in meters squared. So even though we put in standard units, inches and pounds, we're still getting the body surface area in meters squared. Let's look at another patient. This patient has a height 6'3" and a weight 203 pounds. So here, before we can put this in the formula, we have to convert that height to just inches. To do that, we take the 6 feet and we convert it into inches. We have, 1 foot will go on bottom, so that cancels out. 12 inches on top. So 6 times 12 is 72 inches. The feet cancel out. But we do have to add back in the other 3 inches that were there. The 72 inches is just the 6 feet. Plus the other 3 inches gives us 75 inches. So this is a height of 75 inches that we're going to be using in our formula. So our body surface area, again, in meters squared, will be the square root of that height of 75 inches times the weight of 203 pounds over 3,131. So second, square root, 75 times 203 divided by 3,131. We'll close that parentheses and enter, and we get 2.21 meters squared. That is actually getting towards the upper end. About 2.5 square meters of body surface area is getting pretty close to as large as most humans get. So those are our formulas. Now, the next thing we need to do, actually got to open this up off my desktop here. It's called a nomogram. We'll go back here and we'll write that out. An nomogram is a tool that is used all sorts of things. It's used in engineering, estimating, for estimating the amount of materials needed for certain things. It's used in a ton of stuff. The nomogram here uses the same information we've been using. It uses height and weight or mass to estimate body surface area. So the nomogram looks like this. Now on this document, it's a little hard to read. It's a little blurry here, but it is in your textbook. Page 190, it's actually on 2 consecutive pages, page 192 and page 193. So if you need a little bit clearer picture than what the one I have here on screen, you can use that one. Now in this nomogram, this middle section right here, that is extra space. That chart that's there is just put in there to fill an empty space. To make the nomogram work, there had to be different spacings. So the nomogram really only involves this spot, this axis, and this axis. Again, to make things line up, we would have had to have this extra space here, so they just put that extra chart in there to fill the space. It really isn't part of the rest of the nomogram. It's actually a separate chart or separate table we'll use. So let's take a peek at a patient here who has let's say that they have a height of 132 centimeters. Actually, let's do this one. A height of 64 inches. We'll start off with that. And a weight of 115 pounds. So we go to the nomogram. Oops. We need to find the 64 inches in height. So height is over here. So we're going to find inches are on this side here. We're going to find the 64 inches. 64 is right there. For weight, we have 115 pounds. So here's our weight. Pounds is on this side, so we have to find 115. There's 110, 120, 115 is going to be right in there. So then what we do is we need to connect those with a line, or if this is a paper chart, if you're using your book, just put the edge of a piece of paper across there. I'm going to actually use a line. I'm going to go from here, the 164, sorry, the 64 to 115. I'm going to edit that line a little bit just to make it easier to read. Make it a little, make it bright red for one, and we'll make it a little thicker. There. So now, again, this line goes from 64 inches over here to 115 pounds over here. In the middle, we have to see where it crosses. And it crosses between the 1.5 and 1.6. So it looks like it's almost exactly at 1.55, right in the middle, between the 1.5 and 1.6, as far as the body surface area. That column is your meters squared. So the nomogram is stating that person would be 1.55 meters squared for their body surface area, because that's where it crosses that axis. Well, let's double check this to see what the formula would give for that patient. It'd be the square root of 64 times 115 divided by 3131. So second square root 64 times 115 divided by 3131. Close, we get 1.53 is what the formula is giving us. So there, the nomogram and the formula were almost dead on, almost exactly the same for estimating that body surface area. Not always the case, but usually they're pretty close. So let's have another example here. We have a patient whose height is 132 centimeters and weight is 31 kilograms. So let's look that up on our nomogram here, 132 and 31. So on the left side over here, we're going to put this at 132. I'll move this down here, 132, right there. Now we got to be careful with our scale. So this goes from 130 to 140. There's 5 spaces there. So that's 10 pounds over 5 spaces. Each space is 2 pounds. Over here, the 31 kilograms. There's 30. Now this is not 31. That's actually 32. So we're going to go partway in between here. Again, from 30 to 40 is 10 kilograms. There's only 5 spaces. So each space is 2 kilograms. We come in here, we see where it crosses. Well, this is 1.0 and 1.1. Again, it's 1/10 of a square meter. There is 5 spaces, so each space is 2/100 of a square meter. So this is 1.02, 1.04, 1.06 is what that's reading. Again, let's double check that with the formula. So 132 centimeters times 31 kilograms. Those are both metric, so this is over 3,600. So second square root, 132 times 31 divided by 3,600. Close that parentheses, we get 1.07 meters squared. So that is pretty darn close. Now, there are a couple of weaknesses in the nomogram. We're going to do a couple more examples yet. But there's a couple of weaknesses in the nomogram that I want to point out. One is these scales are what are called logarithmic scales. What that means is what this much space means at the bottom of the scale is way different than what that much space means towards the top of the scale. Let me show you what I mean. If I come down here, from here to there is 10 centimeters. There are 10 spaces in between, so each space is 1 centimeter down here. But as we come up here, from here to here is also 10 centimeters. There's only 5 spaces in between there, so each space there is 2 centimeters. So if we continue going up, from here to here is 20 centimeters, from 220 to 240. There's only 2 spaces. So there, each space is 10 centimeters. So what one space is equal to depends on where it is along that scale. That's what the logarithmic scale does, is the spacing changes as we go from small numbers to large numbers. So if you struggle to determine scales and reading scales, the nomogram may not be the best method for you, because you're going to have to determine the scale and set the scale every measurement. You can't just figure out what is the scale here, what does each space stand for, and then just keep using that, because it changes depending on where you're at on the scale, depending on what your numbers are. Now, the second big limitation here, and I've always thought this was really kind of strange and a little bit funny, but it has to do with just how things line up. On the height side of things, you can see it goes up to 90 inches. 90 inches is 7'6". I don't think we're going to run into too many patients. I mean, maybe 1 or 2 in a whole career, if that. You're not going to run into too many patients that are 7'6". Chances that those couple of patients you do run into are going to need a calculation of body surface area are even smaller. But we go over to the weight side here, and it only goes up to 180 pounds. Well, we're going to run into a lot of people that are over 180 pounds. I passed 180 pounds a long time ago. So the weight is not sufficient. If their weight is over 180 pounds or 80 kilograms, we can't use this nomogram. We have to go to the formula or one of the other methods for estimating the size of the person. So let's do another example or two here using the nomogram. Let's take a patient who has a height 2.04 meters and a weight of 75 kilograms. So 2.04 meters. Now remember, we got to change that. That is 204 centimeters. 204. So here's, again, a little bit of a weakness here, because in these larger measurements, the spacings are pretty large. 204 going to be somewhere in there. This is 220. 210 is that center line, so 204 is going to be a little less than halfway up. So I'm going to have to take my line here, and I'll try to move it up there to 204. Somewhere in there. And then we said 75 kilograms. So over here, we need to move this up to 75. Well, there's 60 and 70, so we got to go halfway in between. Not going to be on one of the lines because the one is 64, the other 66. So we're halfway between those lines like that. We're pretty close. We're just a touch off. What we see here, it goes through at 1.9 square meters is the body surface area that it's giving us. So we have 1.9 meters squared. Let's double check that against the formula just to see what it gives us. This is the square root of 204 times 75 over 3,600. Second square root, 204 times 75 divided by 3,600. And we get 2.06 meters squared. So there is a little bit of a difference here. Part of that is because on the nomogram, with these larger numbers, it's a little bit harder to get it lined up perfectly. Neither one of these was lined up perfectly. And this typically is where the nomogram has its biggest errors, is when we have larger people. A larger height and a larger weight, the nomogram seems to be less precise, less accurate compared to the formula. Now, the nomogram can also be used to work backwards. Let's say we have a patient that has a body surface area of 1.1 meters squared. And we know that they have a height. Their height is 160 centimeters. We can find their weight in kilograms. Let's go back here. So their height is known, so let's put the height on at 160 here. There's our 160 centimeters. Now over here, we're going to move this up or down until we hit the 1.1. There's 1.1 right there. So we go through the 1.1. And on this other side here, we see that's 25, 6, 7, 8, 9. We're between 29 and 30 kilograms. Closer to the 29, so we might just say 29 kilograms is where that patient is. So I'm okay saying that we estimate their weight at 29 kilograms. We could do this with the formula, but it's a lot more complex. We're solving an equation with a square root in it, so we have to square it and then isolate the weight. Most of you have done well enough with equations that I'm sure you could do it, but the nomogram is just a little bit quicker way of doing that reverse calculation. Now, the other thing that is in the nomogram, this other chart in the middle here, this is a totally separate chart, totally independent from the rest of the page. It is really not part of the nomogram. It is a separate, like I said, it's a chart of its own. But since we had the blank space in the nomogram, they typically shove it in there just to fill in that blank space. Because in itself, it is a very useful chart. And that is body surface area for children of normal height and weight. Or normal, weight for their height for their weight. Normal height for their weight. The term that is often used here is height and weight proportionate. In other words, does their weight fall into the normal range for their height? Or does their height fall into the normal range for their weight? Whichever way you want to figure it. And so with this, if we just have a child, and this is usually for children, if we have a child's weight in pounds, we can get an estimate of their body surface area. And it's for pediatric doses. Often we want to get it done quicker. Just a little bit quicker way of doing it. So let's say we have a child that comes in that is 34 pounds. We want to find their body surface area. We go to the nomogram. Now again, the scale on this nomogram is logarithmic. At the bottom down here, from here to here is a pound. Oops, wrong marker. From here to here is a pound, 1 pound. Up here, a similar distance is 10 pounds. So we have to be careful how we read that. Now I'm going to get this red line out of it. So this patient was 34 pounds. So we have to come here with the table. This is 30, this is 40. It appears each of those marks is 2 pounds. So 34 pounds would be right here. The other side, right there. Well, again, we have to figure out the scale. This is 0.6 and 0.7. So that is 0.1 meters squared in between there. There are 5 spaces, so we divide by 5. Each space is 0.02 meters squared. So this is the 0.6, 0.62, 0.64. About 0.66 is that body surface area. So that patient, the quick estimate for that child would be 0.66 meters squared of body surface area. So now with that, let's go back to our dosage calculations and bring this into how we calculate those dosages. Now from here on out, I am simply going to use the formula for calculating body surface area. But as you've seen, as long as we're not towards the upper end of both the height and the weight scales, the nomogram will give us pretty much the same body surface area. So you are welcome to use that if you wish. So let's say we have an order to administer the recommended dose. For a patient that is a height of 58 inches and a weight of 92 pounds. And so our recommended dose is given as 45 to 50 milligrams per meter squared per 6 hours. And the label on our supply says that we're looking at 15 milligrams in 4 milliliters. So our first step is going to be to find our body surface area. So it's the height of 58 times the weight of 92. Now these are in inches and pounds, so we're going to divide by 3,131. So, second square root, 58 times 92 divided by 3,131. We get 1.31 meters squared is our body surface area. So that's where we begin our dosage calculation with 1.31 meters squared. And of course, we're going to use the maximum of our range. So 50 milligrams per meter squared. Making sure the meter squared cancels out. And it does. It's on bottom, so it cancels out the meter squared on top. And then our next step, to use our concentration on the label. Milligrams have to go on bottom to cancel out milligrams. So 15 milligrams in 4 milliliters. The milligrams cancel out. On top, we have 1.31 times 50 times 4 milliliters. Oops. Giving us 262 milliliters. Over on bottom, we have 1 times 1 times 15, so that's just 15. So we'll divide that out. 262 divided by 15 gives us 17.47 milliliters. Now we do have to go back. This was per 6 hours. The doctor's order just said recommended dose, didn't specify a time period, so we don't have to adjust the time period. But we do have to make sure we label that as per 6 hours so we know how often to give it. This is also, of course, the maximum allowable recommended dose. We need to go back and find the minimum. So we take that 7.47 milliliters every 6 hours, and we're going to titrate it. We use that one came from the 50 milligrams per meter squared. We want to change it to the 45 milligrams per meter squared for the minimum. And of course, milligrams per meter squared cancels out. We take our 17.47 times 45 divided by 50. We get 15.72 milliliters every 6 hours. So our allowable range is from 15.72 to 17.47 milliliters every 6 hours. And of course, this can go into an IV. So let's say the doctor orders the recommended dose be administered through IV. So let's say our recommendation here is 75 to 80 milligrams per meter squared every 8 hours. The label on our supply is telling us 25 milligrams in 12 milliliters. And our patient is 144 centimeters and 42 kilograms. And I need one more piece of information off of the label, and that is a drop factor. And my drop factor is 18 drops per milliliter. And so we want to find a range of drops per minute here. So again, we need to find our body surface area. I realize we only have like a minute and a half left, so I'm going to fly through this. 144 times 42 over 3,600, since those are metric. Second square root, 144 times 42 divided by 3,600 is 1.30 meters squared over 1. We're going to use the maximum of 80 milligrams per 1 meter squared to cancel out the meters squared, and 25 milligrams in 12 milliliters to cancel out the milligrams, and finally 18 drops per milliliter to cancel out the milliliters. So on top there, we have 1.3 times 80 times 12 times 18 gives us 22,464. That is drops. And on bottom, we have 25 times 1 times 1. So we'll divide that by 25, giving us 898.56 drops. Now we got to bring in the time, that 8 hours, and then we'll have to convert that. 1 hour is 60 minutes. So on top, it's still 898.56 drops. The hours have canceled out. On bottom, 8 times 60 is 480 minutes. So take the 898.56 divided by 480. We get 1.87 drops per minute. Now that is the maximum. We have to find the minimum using the titration. We only have just a few seconds left, so let me give you homework on page 196, 197. 1 through 19, the odds. Practicing these dosages based on body surface area. Monday, we will review all of these dosage calculations that we have done. Remember, next week, Wednesday, will be Unit 3 test. This is the big one, so make sure you're prepared. This is the one where people's grades start to drop a little bit, so That's why we're going to do a day of review on Monday, but also make sure you look ahead and prepare for this one. This is a little bit tougher than the previous two. With that, you guys have a great weekend. Hopefully we'll see you all on Monday.